Now, the last important application of ionic equilibrium concept is the phenomenon of indicators. So, indicators are the substances which are used to follow the course of a reaction, that is completion of a chemical reaction. So, how do they function? They function by color change. Indicators are of types: acid base or neutralization indicators, redox indicators, and complexation indicators. Acid base indicators, they change color with respect to pH. Redox indicators, they change color with respect to the medium, whether it is oxidized phase or reduced phase. Complexation indicators, they change color with complexing phenomenon or simple nature. Depending upon that, color change is observed. Now, our aim is to study only the neutralization indicators or acid base indicators. Important acid base indicators are phenolphthalein and methyl orange. Phenolphthalein and methyl orange. Phenolphthalein is considered as a weak acid. Weak acid can be generally represented as HA. Here phenolphthalein is a weak acid, it is represented as HPH. Since it is a weak acid, you can apply equilibrium, ionic equilibrium. It dissociates weakly to form proton and phenolphthalein anion. Another indicator is methyl orange. So, methyl orange is another indicator. So, here methyl orange is a weak base. It is generally represented as MEOH. MEOH, weak base, means it can be studied as ionic equilibrium as dissociating to Me plus OH minus. Now, how does it function by color change? You will see. So, undissociated phenolphthalein is colorless in nature, whereas phenolphthalein anion is pink in color, whereas methyl orange, the name is called orange because it is an intermediate of yellow and red in VIBGYOR, violet, indigo, blue, green, yellow, orange, red. So, VIBGYOR visible spectrum, it is the intermediate between yellow and red. Actually, methyl orange undissociated form is yellow in color. After dissociation, if the cation is red in color. So, it is red in color, yellow in color, the medium color is given. Here colorless and pink, because the way it is named after the color means there is one another indicator called methyl red. That is why it is, in order to distinguish that, it is called methyl orange. Now, how does it function? If this indicator, let us study the general reaction. Neutralization reaction is any acid plus base giving salt plus water. Simplest example is HCl reacting with sodium hydroxide to form NaCl and water. Here HCl, hydrochloric acid, is colorless, sodium hydroxide is colorless, the formed sodium chloride is also colorless, it is soluble. So, it is not possible to estimate the course of reaction or completion of reaction. To this we add, so following the reaction is called titration, where we take two reagents, one is taken in the burette, another one is taken in the conical flask, then burette is graduated, we are calculating measuring the observed volume, what is the volume added for the completion of reaction. For this, to the contents of the conical flask, we add indicator, small amount of indicator. So, indicator will show its original color. During the reaction, it will change its color. From the change in color, you can observe. Let us illustrate with the example. If for this titration, phenolphthalein is used. So, generally it is general practice to add sodium hydroxide from the burette. HCl is taken in the conical flask. So, in any fashion you can take, all are dilute solutions only. So, here we are illustrating the case, sodium hydroxide. So, to this sample HCl we are adding indicator. If we add indicator phenolphthalein to HCl, so phenolphthalein is colorless in acid because it is a weak acid. Phenolphthalein is a weak acid, undissociated form. Acid means acid is a proton donor. So, enormous protons are absorbed. Due to common ion effect, equilibrium is shifted towards left. If the equilibrium, because HCl provides H plus and Cl minus. HCl is a strong electrolyte. So, hydrogen ion concentration getting increased to the indicator itself a weak acid. So more amount of protons shift the equilibrium towards left. So undissociated phenolphthalein is formed, which is colorless in nature. So phenolphthalein is colorless in acid. Phenolphthalein is colorless in acid. So this phenolphthalein HCl. Acid is nothing but HCl. So it should not be confused with phenolphthalein is considered as a weak acid. That is separate. That is separated. But it is mixed with a strong acid, hydrochloric acid. In this combination, the conical flask contents are colorless. From slowly sodium hydroxide is added. When sodium hydroxide is added, sodium hydroxide is a base. So it is a strong base. When sodium hydroxide is added, it gives strong base, means readily dissociates, forming hydroxide ions. These hydroxide ions combine with H plus. It is a weak equilibrium. H plus forming water. So hydroxide ions are forming water. So in this setup, H plus is removed. Phenolphthalein anion is generated. So added OH minus removes the H plus as water. Phenolphthalein anion is generated, means it turns pink. So if you add sodium hydroxide from the burette, it turns pink. Original color is colorless. It turns pink, or in other words, appearance of pink color is the end point. Appearance of pink color is the. So in these cases, we call a term called, you are aware of the term. What is meant by end points? End point is the instant at which there is a color change, colorless to pink, yellow to red, whatever be the case, from one color to other color. The instance at which, the point at which the color of the system is changed, that is called end point. So each indicator is possessing some end point. The end point of phenolphthalein is change in color from colorless to pink or pink to colorless. And alternatively, if you take sodium hydroxide in the conical flask, sodium hydroxide plus phenolphthalein, phenolphthalein is a weak acid. So this reaction, this H plus and OH minus are removed, it becomes pink. Conical flask contents are pink. To this pink, if you add HCl from the burette, it becomes colorless. It becomes colorless. If it becomes color, that is, in that case, it is called disappearance of pink color. Appearance of pink color or disappearance of pink color. So this explains the function of phenolphthalein as the indicator. Here phenolphthalein is, all the color changes are observed, explained only by this equation. Whether they are due to common ion effect, whether the equilibrium is shifted towards left or right, accordingly color change takes place. We will see the limitation of this indicator bit later. Before that, the second indicator also let us see, methyl orange. So methyl orange is considered as a weak base. So in the similar manner, if you add acid, strong acid, if the strong acid is added, strong acid provides H plus. So H plus immediately recombines with OH minus, giving water. So methyl orange cation is generated, the system becomes red. The system becomes red. If it is added to a base or alkali, OH minus concentration is increased. OH minus concentration shifts the equilibrium towards left, so it renders yellow. So the solution is yellow in alkaline medium and red in acid medium, or in other words, to consolidate, phenolphthalein is colorless in acid and pink in alkali. Methyl orange is yellow in alkali and red in acid. In none of the cases it is orange. It is an intermediate between yellow and orange, yellow and red. That is why it is called. So these are the cases. In all these cases, we explain only with respect to strong acid, strong base. The question arises, if one of the component is weak, what happens? So both the indicators can be used if acid as well as base is strong. Here we have illustrated only with HCl and NaOH. What happens? HCl and Na2CO3 or oxalic acid and NaOH. In that cases, these are the different combinations. So each has importance. This is strong acid, strong base combination. Here acid is strong, but sodium carbonate is a weak base. Here acid is weak, sodium hydroxide is strong base. So that is to be noted. Three type of titrations. So strong acid, strong base titrations can be used with any indicators because both they are the good suppliers of H plus and OH minus, so that the equilibrium is shifted or the respective cation or anion is formed, showing the color change. But if it is used with the sodium carbonate, let us check whether sodium carbonate versus HCl titration can be held with a phenolphthalein indicator. We are going to check. Actually, the answer would be no. So we are going to check whether phenolphthalein can be used with the titration for the titration between sodium carbonate and HCl. Sodium carbonate is a base. HCl is the acid. So phenolphthalein, we have seen that phenolphthalein is dissociated H plus pH minus. It is a weak acid. So phenolphthalein is colorless in acid. We have seen it is colorless in acid and pink in alkali. We have seen. So here the alkali is sodium carbonate. Pink color, how it is generated to be noted. Pink color is generated because of phenolphthalein anion. So it will not be so pink if it is put in sodium carbonate. So there will not be color change. Why? Because if sodium carbonate is a weak base, sodium carbonate weakly dissociates to form sodium hydroxide and carbonic acid. Here the base is strong, carbonic acid is a weak acid. Base is strong and carbonic acid is the weak acid. So here also weak acid, here also weak acid. Phenolphthalein itself also weak acid, carbonic acid also weak acid. Then how can it donate protons to shift the equilibrium towards left or right? So it is not functioning. So phenolphthalein cannot be used for weak acid titrations. If it is used with weak acid titration, the color change is not observed. So for this titration, better choice is only methyl orange. So methyl orange is the indicator. So that methyl orange means, why? How does it hold okay? Methyl orange splits as Ma plus and OH minus. Here HCl is strong. HCl is strong. In this titration, HCl is strong. Strong means readily donates protons. Protons combine with hydroxyl ions forming water. Here this red color is observed. So the equilibrium cannot be shifted towards left or right if the one of the component is weak. That is the limitation. So phenolphthalein as a whole, from this you might have studied, you have to note that phenolphthalein cannot be used for the titration involving a weak base. Similarly, methyl orange cannot be used for the titration involving weak acid, such as acetic acid. So for the second titration, methyl orange cannot be used, phenolphthalein can be used. For the first titration, methyl orange can be used. So here HCl and NaOH, any titration can be used. So this is one type of limitation of indicator. Also this limitation of indicator has been studied only with respect to ionic equilibrium by considering them as weak acid or weak base. So here these are indicators used for particular type of titrations. Lastly, there is a type of indicator called universal indicator. So these are individual indicators which are used either in alkaline medium or in acid medium. Universal indicator is one which is a mixture of different indicators. Universal means collection. Mixture of different indicators, reasonable mixture, which shows color change in different pH. So they show different colors in different pH, or in other words, original color is different, its color is different in different pH, or in other words, the substance changes its color with respect to pH. That such indicators are called universal indicators, so that they can be used over a wide range of pH. So these are the important applications. Lastly, want to consolidate the aspects of salt hydrolysis and indicators and also buffers. These points to be noted in solving the problems as well as meeting the different requirements. One is another form of Henderson equation. Henderson equation of a buffer. Henderson equation of acidic buffer. Henderson equation of a this is alternative form of Henderson equation. That's all. Acidic buffer is given by 7 minus of pKa. This is for acidic buffer. Acidic buffer. This one is called basic buffer. pH of a acidic buffer or basic buffer is given by 7 minus pKa plus concentration of acid. Or in other for pH of a basic buffer is 7 minus of pKb plus concentration of base. Ka is a dissociation constant of acid. Kb is the dissociation constant of base. pH. So we know that here it has to be noted. It is 7 plus, that one is 7 minus. Because here acidic pH is less than 7. Basic pH is greater than 7. Neutral pH equal to 7. That is to be noted. Neutral pH is 7. Solutions are divided into 3 types based on pH as. So these expressions enable the determination of pH of a buffer, whether it is acidic buffer or basic buffer. Lastly, what is the pH of a solution if it is made up of both the components weak? Let us take this ammonium acetate, NH4 COO CH3. Ammonium acetate is a combination of ammonium hydroxide and acetic acid. Ammonium hydroxide and acetic acid. Ammonium hydroxide is also weak base. Acetic acid is also weak acid. Both are weak electrolytes. In such cases, the hydrolysis constants are to be noted. This we have seen. KH equal to KW by Ka into Kb. This relation we have noted already. This is to be used if both the components are weak. If one of the components are weak, either Ka or Kb. These points are to be noted with respect to pH of buffer solution. These are alternative forms of Henderson equation and salt hydrolysis phenomena which enable the determination of pH. Lastly, this solubility product. Solubility product varies from system to system. So, based on the solubility product, we can predict whether the system is soluble in water or precipitated. Let us illustrate. AgCl. AgCl concentration is written as Ag plus solubility product of AgCl is Ag plus concentration into Cl minus concentration. We don't know the solubility. Let us assume S is the capital S is the solubility. So S moles soluble means they form each S mole of silver ion, S mole of chloride ion. So concentration of silver plus, because this is the equation, AgCl giving rise to Ag plus Cl minus. So it form, if it is soluble, it will form S plus is the concentration of S is the concentration of Ag plus. Another S is the concentration of Cl minus, because 1 mole dissociates to form 1 mole each of silver plus and chloride ion. Then S moles will dissociate to form S moles each of silver plus, and so Ksp equal to S squared or S equal to root of Ksp. So from the knowledge of solubility product, it is possible to determine the solubility of a substance. So this is to be noted. So what is the significance of solubility product? Already noted. It is to be noted. If the solubility product exceeds or deficit of ionic product, accordingly precipitation or dissolution of the particular stock takes place. That is to be noted. This with respect to solubility product. So far we have consolidated different aspects of ionic equilibrium. Now we can do some sums and questions in these lines. We will see some questions on chemical equilibrium as well as ionic equilibrium. First on chemical equilibrium, this sum reads as, it is based on the calculation of equilibrium constant, that is Kc. So this sum reads that 28 grams of nitrogen and 6 gram of hydrogen. So 6 gram of hydrogen, 28 grams of nitrogen are kept in a 1 liter vessel which is maintained at 400 degrees C. So 400 degrees C, this mixture was allowed to establish equilibrium. The equilibrium mixture contains 27.53 gram of ammonia. 27.53 gram of ammonia. The approximate value of Kc, that is equilibrium constant for the reaction, they have given formation of ammonia. N2 plus 3H2, it is chemical equilibrium. N2 combining 1 mole of nitrogen combining with 3 moles of hydrogen forming 2 moles of ammonia. So here they have given the initial amounts. 28 nitrogen and hydrogen were mixed. So initial concentrations are given. So the system is allowed to approach equilibrium. So how will the equilibrium attain? So they are mixed. Nitrogen will start reacting with hydrogen. Some amount of ammonia will form. So this reaction continuously proceeding. When considerable ammonia has been formed, the formed ammonia will start dissociating to give back nitrogen and 3 moles of hydrogen. So when this system continuously taking place in either direction, at one instance the system is said to have approached equilibrium. So if it is having approached the equilibrium, you can determine the equilibrium constant. So first, the expression for equilibrium constant Kc equal to product concentration ammonia raised to its stoichiometric power 2 divided by reactant concentration nitrogen into hydrogen raised to its stoichiometric power 3, stoichiometric cube, H2 cube. So Kp or Kc can be written. Kc is written as concentration of ammonia squared divided by concentration of nitrogen squared, nitrogen into concentration of hydrogen cube. So concentration of, this is the expression for Kc. So here concentration means it is to be represented number of moles. We have to calculate. So first we have to calculate initial concentration, then equilibrium constant. There are stages. First calculation of initial concentration, because initially concentration of ammonia is 0. They are just mixed. Nitrogen and hydrogen are mixed. Means that no formation of ammonia initially. So so you can rewrite the equation and compare what are the concentrations at different instants. Initially 28 gram of nitrogen is there and 6 gram of hydrogen is there. There is no formation of ammonia. And after the reaction proceeds, nitrogen amount goes on reducing, hydrogen amount goes on reducing, ammonia amount goes on increasing. At certain states, some fixed amounts of nitrogen, hydrogen and ammonia are formed because of simultaneous reactions on either side, forward reaction as well as backward reaction. First let us see the concentrations in the, what is meant by concentration? Concentration is moles per liter. 1 liter vessel it is given. So the unit of concentration is moles per liter. Concentration is represented as moles per liter. Then how to calculate the number of moles? Number of moles is nothing but weight divided by molecular weight divided by volume. So the concentration is calculated in this fashion. Weight divided by molecular weight is number of moles. So number of moles divided by volume in liter. So one by one let us calculate. So nitrogen formula, nitrogen atomic number 7, atomic weight is 14, 1 nitrogen is 14, 2 nitrogens 14 into 2. So this is the molecular weight of nitrogen. And hydrogen atomic weight is 1 and molecular weight is 2 into 1, 2. So molecular weight of hydrogen is 2, molecular weight of nitrogen is 28, molecular weight of ammonia. Ammonia is nitrogen is 14 plus nitrogen atomic number is 7 but atomic weight is 14. So 14 plus 3 into 1 hydrogen is 1. So 17. So 17 grams of ammonia constitute. So this is the molecular weight. So weight divided by molecular weight. First, number of moles of nitrogen. Number of moles of nitrogen is nothing but divided by weight divided by molecular weight, total divided by volume. Volume is always 1 liter. They are kept in 1 liter. That renders the problem easy. This can be reduced just by weight by molecular weight. Anything divided by 1 is the same number. So weight divided by molecular weight. So here weight of nitrogen is 28. Molecular weight of nitrogen is also 28. The volume is 1. So moles per liter, 1 mole per liter. 28 by 21, 28 divided by 1 is 1 mole per liter. Now for hydrogen, hydrogen 6 grams are taken. So 6 gram divided by its molecular weight is 2. Total divided by 1 liter. So 3 moles per liter. Hydrogen is 3 moles per liter. Rewriting the equilibrium, N2 plus 3H2 giving 2NH3. The initial concentration we have found. Nitrogen initial concentration is 1 mole. Hydrogen initial concentration is 3 mole. But initially there will not be formation of ammonia. Initial concentration of ammonia is 0. Let us assume that X moles have reacted in time T. So X is the amount of nitrogen reacted in time T. So according every mole of nitrogen will consume 3 moles each of hydrogen to form 2 moles of ammonia. So out of 1 mole, X mole has reacted. What is the unreacted concentration? So unreacted concentration is the equilibrium concentration. Unreacted concentration is the equilibrium concentration. So unreacted concentration is 1 minus X. 1 is the total concentration as per the stoichiometry, 1 mole, and X is the amount reacted, number of moles reacted. Unreacted moles of nitrogen is 1 minus X, whereas here it is 3 minus 3X. So because every mole of nitrogen will consume, so it should not be confused with this 3 and everywhere it is 3. Here nitrogen 1 mole also coming, hydrogen for this case they have given 3 moles. As per the stoichiometry, 1 part of nitrogen consumes 3 parts of hydrogen. So 1 means X moles have reacted means here there is 3X moles of hydrogen have been consumed and 2X moles of ammonia would be formed. It is just a proportion. So X is the amount reacted in time T in general. X is the amount reacted in time T in general. But for nitrogen 1 part X is reacted. But for hydrogen 3 parts 3X is reacted. Ammonia formed. Ammonia is not reacted. Ammonia is formed. ammonia formed is 2x parts. So these are the concentrations. 1 minus x is the equilibrium concentration of nitrogen. 3 minus 3x is the, because 3 is the initial concentration, 3x is the reacted, unreacted concentration is 3 minus 3x. 3 minus 3x is the concentration at equilibrium, concentration of hydrogen at equilibrium. So 2x, because so 2x has been formed. X is reacted means 1 part reacted, only 2 parts are formed. 1 part reacted, only 2 parts are formed. 2x moles of ammonia are formed at equilibrium. But here in the sum, amount of ammonia is also given. Amount of ammonia formed is 27.53 gram of ammonia is said to have formed. Its molecular weight we have calculated as 17. So 14 plus 3, 17. So this is the value. This is 1.62 mole per liter. So number of moles of ammonia formed is moles per liter. It is 1 liter vessel only. So the number of mole of ammonia formed is 1.62 moles. But as per the equilibrium, we have seen that 2x is formed. So for 2x is the amount of ammonia formed, 1.62 is the number of moles of ammonia formed, which means that 2x equal to 1.62, or in other words, x equal to 1.62 by 2 equal to 0.81. So mole per liter, x is the amount reacted. So we have to substitute. We have found x. Now once again rewrite. Equilibrium concentration of nitrogen is 1 minus 0.81 and that of hydrogen is 3 minus thrice 0.81 and that of ammonia is 2 into 0.81. So 2 into 0.81 we have seen. Then we know the expression Kc equal to, already we have written, Kc equal to ammonia squared, concentration of ammonia squared divided by concentration of nitrogen into concentration of hydrogen whole cube. So what all we have substituted? We have to, so 1 minus 0.81 is nothing but nitrogen concentration, and this one hydrogen concentration, this one ammonia concentration. These have to be substituted here. So substitution of these gives value equal to 75. Substitution, directly numerals are given. So there are different choices given in this sum. Now we have found the value of Kc. So actually the question I asked is the Kc value. There are 4 choices given for Kc value: 75, 50, 25 and 100. So out of these, 75 is the correct choice. First 75 is given as first choice in the current question. So first choice is the correct answer for this question.